So today I want us to talk a little bit of differential calculus. So let's give this one a good look. They say the graph of g of x equals ax cubed plus bx squared plus cx. A cubic function having a y-intercept of 0 is drawn below. The x-coordinates of the turning points of g are -1 and +2, respectively, as we can see from this nice sketch. So the first question says, for which values of x will this function increase? So every time if we must talk about the intervals of increase or decrease, we go to the x-coordinates of the turning points. So we want to see what is happening on either side of these x-coordinates. So let's go to -1. If we look on the left of -1, meaning from -infinity up until -1, the function is decreasing. So it's not the solution we are looking for. But now if we look from -1 all the way to 2, we can see the function is increasing. So it's the right solution. But if we focus on 2 all the way to +infinity, the function is decreasing again. So where is it increasing? Any value of x that is between -1 and 2 like that. So how do you say between in mathematics? You say any value that is less than 2, but greater than -1 like that. Alternatively, you could have said from -1 all the way to 2 like that. So it's where your function is increasing. But if they wanted to know where is it decreasing, you'll tell them it's decreasing for any value of x that is less than -1, or it's decreasing for any value of x that is greater than 2. The alternative notation for this, you can say from -infinity all the way to -1 in union with from +2 all the way to infinity, like that. So those are your intervals of increase and decrease. And then you are set. So let's look at the second question then. It says, write down the x-coordinate of the point of inflection of this function. So we know at the point of inflection, it's where the second derivative is equal to 0. So meaning under normal circumstances, we are supposed to differentiate the function twice, equate the second derivative to 0, then solve for x. So the value of x we find is the x-coordinate of the point of inflection. So when I say under normal circumstances, I mean if we are given the equation of the cubic function itself. So in this case, we don't have the equation. We need to work with what we have. So we understand that the point of inflection is a point that is halfway through your two x-coordinates of the turning points like that. So in simple language, I'm saying the x-coordinate of the point of inflection, it's just going to be the midpoint of your two x-coordinates of the turning points like that. So you'll say the first x-coordinate is -1, and then you add this to 2, then you divide the result by 2. So this means the x-coordinate of the point of inflection, it's just going to be +½ like that. So that's the concept for this one. And then you are set. It's the midpoint of your two x-coordinates of the stationary points or the turning points if you prefer. That's fine. Now let's look at 8.3. It says, for which values of x will the function be concave down? So we also know at the point of inflection, it's where the function changes concavity. So for this one, which is sketched, It's going to be a point where the function changes from being concave up to being concave down. So at exactly half, the function will change. So what am I saying? I'm saying all the way from negative infinity up until half, the function is going to be concave up. But the question said, where is it concave down? So it's going to be concave down all the way from half up until positive infinity like that. So concave down meaning it's facing up. So that's how you tell them. You'll tell them the function is concave down for any value of x that is from positive half all the way to positive infinity. But if you prefer, you can say it's concave down for any value of x that is greater than a half, like that. Yes, and then you are set for this one. Over and out. Okay, that's fine. So let's look at 8.4. They say if g prime of x is negative 6x squared plus 6x plus 12, determine the equation of g. So what are they doing here? They give you the equation of the derivative, which is a quadratic function, and then they expect you to find the equation of the cubic function itself. So I think we need to go to the whiteboard for that. Yeah, let's go to the whiteboard. Okay, we have arrived. So this is what they told us. They said, if g prime of x is negative 6x squared plus 6x plus 12 like that, so determine the equation of the cubic function itself. So for this one, we don't need to do much. Why? Because we know from the statement they told us g of x equals ax cubed plus bx squared plus cx, like that. So ours is to differentiate this cubic function. Then we understand that this derivative is equal to that derivative. So if the derivatives are equal, then it means these parts as well, they need to be equal. So we are just going to equate the coefficients for this one. So differentiating the original function using the power rule, we get 3ax squared, and then we say plus 2bx, and then we say plus c, like that. So now we equate the coefficients. If the two derivatives are equal, then negative 6 has to be equal to 3a. So this means the value of a will just be negative 2, like that. And then you'll say positive 6 has to be equal to 2b, like that. So it means the value of b is supposed to be positive 3, like that. So c is just a constant. It's also equal to the constant in this derivative. So then you'll tell them, okay, this means g of x is supposed to be ax cubed, and then you say plus bx squared, and then you say plus cx, like that. So this is the equation of the cubic function, like that. Yes, there's not much you had to do for this one. It was a matter of differentiating the original function and then equating the coefficients. So you'll do this every time they gave you the function of the derivative, and then they expect you to find the cubic function itself. Easy enough. Okay, that's fine. Now, let's look at the last question, the most interesting one. And this paper holds a very special place in my heart because it was actually written by myself 3 years ago. Not bad. So 8.5 says, determine the equation of the tangent to this function that has a maximum gradient. Think of that. So we don't know what is the value of the gradient, but we know it's a maximum. So meaning we are maximizing the gradient in this question. So we know and understand that if we must find the tangent, or rather the equation of a tangent to a function, we don't know where it's going to be. But we know that we need to have the gradient. We also need to have a point of tangency. So how are we going to approach this one? If we look at g prime of x, we understand that g prime of x is the derivative of the function, but most importantly, it's the gradient or the slope of the tangent line to the function itself. Are we fine? So that's the concept we are going to use. So we are saying this g prime of x, the whole of this, it's actually the gradient of the tangent line. So now we have the gradient, but now they are saying the gradient of the tangent line to this function has to be a maximum. So meaning we have to differentiate this gradient, equate to 0, then solve for x. The x value we find, it's going to be the x coordinate of the point of tangency. Then what do we do with that x coordinate? We substitute it into the original function to find the corresponding y value. So now we have a point of tangency. And then when we are done, we take the very same x value, we substitute it into the derivative so that we can find the exact value of the gradient. You have the gradient, you have the point of tangency, you are set. You can find the equation of a tangent now. So enough with the talking. Let's do the actual working. So we know this is g prime of x. It's the gradient of the tangent line. But they said this gradient of a tangent line must be a maximum. So meaning we differentiate the gradient. So in doing so, using the power rule, we get negative 12x plus 6 like that. But they said this gradient has to be a maximum, so we equate this to 0. Then we take 12x to the other side, it becomes positive like that. Dividing both sides by 12. So your x will be 6 over 12, which is just going to be positive half like that. That's fine. This is the x coordinate of the point of tangency. So we come back and say, what is g of half? So remember, we want to find the corresponding y value so that we have a point of tangency. That's what we said. So let's see how much we get if we put everything into the calculator like that. So we are just going to get 13 over 2. So this means the point of tangency is going to be where x is half, y is going to be 13 over 2. But now we need to find the exact value of the derivative. So we say, what is g prime of half? We need to know the gradient of the function at the end of the day. So we substitute it into the derivative itself. And let's see how much is the gradient of this tangent line. So we find that the gradient will just be 27 over 2 like that. So from here we understand a tangent is just a straight line And its equation has to be in the form y equals mx plus c. So we come back and say, what is the y value of the point of tangent c? We found it to be 13 over 2. And then what is the value of the gradient? It's 27 over 2. What is the x-coordinate of the point of tangent c? We said it's going to be half. We are looking for the value of c. So let's see how much is 13 over 2 minus 27 over 2 multiplied by a half, like that. So we find that c, which is the y-intercept, it's going to be -1 over 4, like that. So this means the equation of the tangent line is just going to be y equals m, which is 27 over 2, x, and then you say plus c, which is just going to be -1 over 4, like that. And then this is just how you had to find the equation of a tangent to a function that has a maximum gradient. So I really hope this video helps a lot. So if you really did enjoy it, please give it a thumbs up, a like that is. Please subscribe to my YouTube channel and please turn on the notification bell so that you don't miss out on any video I post. But thank you so much for watching. Let's see you in the next video.